Welcome, friends. So, in the last part of this session, we have discussed star network and its numerical demonstration. Now, with the continuation of the previous topic, we discuss at this part of this academic course, which is network theory, we shall discuss delta load, delta network. In the delta network, previously we have found that line voltage and phase voltages are all same, and line current becomes root 3 times phase currents. And when it comes to the power measurement of the delta network, the same principle applies. If we have a 3-phase delta network, we require to measure overall power of the delta network. And again, how the connections of the wattmeters are done, based on that wattmeter readings will change accordingly. So with this background, let us proceed towards the delta network load or delta connected load. So let us consider figure 9, where again 3 loads are connected in a delta fashion. Now what is delta fashion? You see, if there are 3 loads are connected in this way, then this is called actually delta network. So this node is connected to this. Again, this node is connected to this node, and lastly we have this node is connected. So it becomes a delta network. It's like this structure. So now current flowing through each load is IR. This is IR, this is IY, and this is IB. So they are all IR, IY, IB, they are all phase current. And similarly, we have current flowing through the current coils. There it is actually IRB, IYR, and lastly we have IBY. These are called line currents. So now if you carefully look that if you carefully look into this figure, that you see this node is IRB is entering, this current is entering, and this IR is leaving, and you see from this side IB is entering. So basically this current IB is flowing to this side. So this is, so there are, with respect to this node, 2 currents are entering. First current is I, RB, plus IB, which is equal to IR. So therefore this current IRB, which is equal to IR minus IB. So applying with the same principle, what we have done in case of a voltage phasor diagram, in case of a star network, we will evaluate what is IRB. This is IRB because this is IR, this phasor is IR, this phasor is IB. So when it is produced in the negative direction, the phasor summation of IR and minus IB is IRB. And similarly, this current IYR is this. When R phasor is produced in the negative direction, so it becomes minus IR. Then phasor summation of minus IR and IY, it will become IYB. So it is directed along this direction. So now the wattmeter 1, the current coil will measure IRB and the pressure coil will measure. The pressure coil is connected across R phase and another is connected B phase. So it is measured basically RB, voltage across the terminal RB. So we need to measure the angle between these two phasors, VRB and IRB. So where VRB is this and IRB is this. So VRB and IR, this angle, it should be 30 minus phi. So this angle should be 30 minus phi. On the other hand, wattmeter 2, current coil will measure for wattmeter 2, this current coil will measure IYR, and for pressure coil it is measuring VYB. This is Y and this is P. So it is measuring VYB. So we need to calculate the angle difference between VYB phasor and IYR phasor. So where is VYB phasor? VYB phasor is this phasor, actually VYB phasor, and IYR phasor is this. So basically so this angle this is phi, no doubt. So this angle is actually 30 plus phi. So this total angle is 30 plus phi. So this angle between VRB and IRB is 30 minus phi and this angle is 30 plus phi. So if you write the accordingly equation for wattmeter 1 reading, which is P1, that is equal to VRB, which is equal to VRB into IRB, and angle between them is cos 30 minus 5. So VRB is the line voltage, IRB is also the line voltage, and the angle between them is cos 30 minus 5. So this is the reading for P1. And if we have the P2, the reading, so first voltmeter reading is VYB, the current reading will be IYR, and the angle between them is cos 30 plus phi. So VYB becomes line voltage, IYR becomes line current, and the angle between them is 30 plus phi, so it is cos 30 plus phi. So we are experiencing the same result that we observed in case of a star network, where P1 was VLIL, that means we observed P1 as root 3 V phase I phase cos 30 minus phi, and we have observed P2 as root 3 V phase, I phase, cos 30 plus 5. So exactly same result we have seen, we are observing here also. So we can expect same result. So if you add P1 plus P2, if you add P1 plus P2, it will give you 3 V phase, I phase, cos phi. Now the individual power consumption in respective phases. So this is the R phase, this is Y phase, and this is B phase. Now for R phase, actually you see the line voltage and phase voltage all are same, so it does not matter. So it becomes VL, and IR becomes IL by root 3. IR becomes phase current. This IR becomes phase current, it is flowing to the respective phase load connected in each phase. So IR becomes IL by root 3 and power factor is cos phi. So similar relation we can observe. So what is the total power consumed? It will be coming as root 3 VL IL cos phi, or maybe we can write in terms of phase voltages 3 V phase I phase cos phi. So in case of delta network, we have also seen that if two wattmeters are connected, then the total power consumed using delta network or delta connected load is sufficient. So irrespective of the type of the load, whether it is star connected load or delta connected load, if we connect two wattmeter, it can measure overall power consumed in that load. Now to demonstrate with a delta connected load, let us have this problem. A three-phase impedance of a delta connected load is 15 plus J20 ohm. So Z load is equal to 15 plus J20. If you evaluate its impedance, it will become 15 square, 20 square under root, and angle is tan inverse 20 by 15. So if you solve this, so the magnitude, this will come 25, this will come 25, and this will come 53.2 degree roughly. So if you solve this Z load or load impedance, it will come for 25 ohm at an angle of 53.2 degree. So what is the line current? You need to evaluate line current. If the applied voltage is 400 volt, so this becomes line voltage. 400 volt is always a line voltage, and also you need to calculate the power consumed. So you need to evaluate IL first, then power. These two parameters you need to evaluate. So let us solve. First we have solved what is ZL, which is 25 at an angle of 53.2 degree. Now from this line voltage we can directly write phase voltage is also 400 volt, because for delta connected load line voltage is equal to phase voltage we have observed. So from that result we can directly write I phase, that is the phase current becomes phase voltage divided by ZL, that is the load impedance connected in each phase. So which is phase voltage is 400 volt for a delta connected load, and Z load connected in each phase is 25 ohm. So if you solve this, it will come 16 ampere at an angle of minus 53.2 degree. So the phase current, magnitude of the phase current is 16 ampere. So if you evaluate line current, it will become root 3 times phase current. So if you solve this, root 3 into 16, so it will become line current as 27.7 ampere. Now coming to the power consumed, it can be again calculated in two different ways. First of all, we have a load having R and L. R is 15 ohm and L is, or X is J20 ohm. Now power is always dissipated in this resistance as mentioned previously. So 15 square into I, sorry, not 15 square. The power consumption is I square R. So I is 16 because phase current. So it will be 16 square into 15. So it is power consumption in single phase. So if you multiply it with the 3, then it will be the total power consumption. So it will be 3 I square R. So if you solve this, you will get 11.52 kilowatt. This is number one approach. And second approach should be using this formula, root 3 VL IL cos phi. So what is VL? VL is 400 volt. What is IL? We have evaluated this one as 27.7. And this cos 53.2 degree. So that is the power factor angle which we evaluated. If you solve this, you will get the same result, which is 11.52 kilowatt. So in case of a delta network, we have seen that power is total power rather consumed actually by the resistance. So it is actually given by 3 VI cos phi or root 3 VL IL cos phi. So 2 wattmeters are sufficient to measure that power. So with this, we have covered most of the topics involved in this three-phase network. We have started with the generation of three-phase wave, and thereon we have compared different systems with three-phase system and understood the three-phase system is superior, advantageous over other systems. Thereon we have started star connection, we have started understanding delta connection, and we have understood the fundamental relationship between phase voltage and line voltage, phase current and line current for both star connected and delta connected network. Subsequently, we have understood how power is measured, and we have understood if there is three-phase network, then 2 wattmeter method is essential to measure the total power consumed by this network for both star network and delta network. And we have also seen a very interesting fact that the same network, if we connect wattmeter and if we change this connection diagram, the wattmeter readings will be different. So, and we have solved several other problems as well. So with this, I am ending here. Some more topics are remaining that till now we have discussed, that is for balance load. Now, our electrical system is not always balanced. The load may be unbalanced as well. So for those unbalanced load, how the power is measured? That topic is left. So in the next session, before concluding this module, that topic, that is the power measurement of unbalanced load, is left. So in the next session, we shall discuss that topic, how power is measured using 2 wattmeter methods, of course, for an unbalanced load. Then this module will end. So till now we have covered most of the topics, so I am ending here. Thank you.